Okay, great.
All looks good.
Okay.
Okay, great. So thanks very much to the organizers for the invitation to present at this meeting. I've not been able to attend all the sessions, but that I've been able to attend, I'm very impressed by the breadth, sophistication of the modeling that's going on. So it's a very exciting time, I think, in this area. So I was asked to give a presentation on radiation hydrodynamics. And so I've decided to try to give an overview, and I thought the best way to start the overview would be with a brief discussion of the motivation. Probably doesn't need very much, but I think one of the easiest motivations is to go back to Shakur's I-73 for a alpha disk model. You can calculate that the radiation pressure exceeds gas pressure within a couple of hundred gravitational radii of a black hole accreting around Eddington. And obviously, when that's true, radiation pressure and radiation dynamics is extremely important and must be included in the modeling. And so basically, it's clear that radiation needs to be included in dynamical models whenever the luminosity of the accretion flow is, say, 10 to the minus 2 of Eddington. At that point, there'll be some region where it's getting to be radiation dominated. And in fact, radiation is important at even lower luminosities because it's very important for energy transport. For example, Compton cooling in the corona of the disk requires proper photon transport. And in addition, when the plasma is only partially ionized, then you can greatly increase the opacities above electron scattering opacities, which is what's used to calculate the Eddington ratio. And that then means that the photons are much more important for the dynamics. And for example, you get line-driven winds. And so it's pretty clear, I think, to everyone that let's see, my forward button is not working here. Interesting, there we go. It's pretty clear that the radiation is really important for modeling accretion on a compact object. So I've tried to give an overview in this talk. I'll try to give an overview on the computational methods and issues for radiation hydrodynamics. I won't focus so much on our own work. Obviously, I can't review all the progress in the field. So I'm going to be very selective, and I apologize to those who've been working in this field if I don't reference your work in this talk. Of course, similar methods and issues apply to neutrino transport, but that'll be in the next talk. I won't discuss neutrino transport specifically in this talk. So a quick outline, I've just given you a motivation. I'm going to focus much of my talk on numerical methods. I'll discuss tests of the methods, and I'd like to spend some time pointing out some challenging issues for the future and give you a quick summary at the end. So methods. So just laying out the problem sort of in its most basic form, sort of mathematically, we have to solve the equations of relativistic hydrodynamics, and so usual form here, where the only thing that's perhaps new is this radiation stress energy tensor, which appears. And this tensor is composed of moments of the radiation specific intensity I nu. And so given the specific intensity, and in fact, I nu over nu cubed is the invariant quantity in relativistic dynamics, given it's basically the photon distribution function. Given the photon distribution function, you can take its moments and then feed that back into the dynamical equations and evolve the system. Now, of course, we need now an equation to evolve the specific intensity as well. This is not a closed system by itself. So you need the rate of transfer equation to close the system. And in an invariant form, it's this form here, where there are source terms on the right-hand side for thermal emission and effective emission due to scattering, and also sink terms due to absorption and scattering. And while this equation looks nice and somewhat simple here, actually, a lot of the complexity is built into this convective derivative here along the path length S. So you need to take this derivative along many, many path lengths, so basically along many, many angles to get the full angular distribution of the radiation field in all directions. And only then, when you've sampled the radiation field in momentum space, can you then take its moments. And so, much like the problem in plasma physics, calculating this distribution function over all of phase space is what's challenging here. It's very, very expensive to solve this equation. It's a very, very multidimensional problem. So for that reason, most people look for simpler methods than solving the transfer equation directly and then coupling it to the hydrodynamic equations. And to find approximate methods, it's useful to adopt the fluid frame. And in that frame, the radiation stress tensor can be expressed as radiation energy density, fluxes, and the pressure tensor. So in the fluid frame, you can sort of decompose the tensor into these blocks composed of this tensors and scalars and vectors. And then all of our ignorance, if you like, can be buried into this radiation pressure tensor in the fluid frame. Basically, you can construct a new tensor called the Eddington tensor, which it just tells you the geometry of the radiation field. It basically tells you the anisotropy of the pressure tensor, just normalized by this radiation energy density. And so the challenge then becomes calculating what this Eddington tensor is. If you know F, you can then compute this pressure tensor and then evolve the fluxes and energy density according to the dynamical equations. So approximate methods really are about building approximations to F. That's one way to think about it. For example, you can even think of the Eddington approximation as one of the simplest you could adopt. You just say that the Eddington tensor is diagonal and isotropic, components are 1/3 along the diagonal, and that's valid for very, very optically thick flows where the radiation field is isotropic. So the first general, approximate method I'll discuss is flux-limited diffusion, which really is only being applied to non-relativistic flows because it involves a diffusion operator, and that's problematic in relativity. And so it's been used a lot in non-relativistic flows, where basically you just assume the radiation flux given by Fick's law is proportional to the gradient of the energy density, where there's some functional form in the front, lambda, where lambda is a function of the radiation energy density. That's a flux limiter that prevents superluminal transport. Basically, it reduces the flux in optically thin regions so that you don't get superluminal transport. And with this ansatz, with this substitution, you eliminate the flux from the problem, and you just reduce the problem to basically two scalar equations, to two temperature diffusion in the non-relativistic regime. You basically have an equation for the fluid energy density and the radiation energy density. And FLD has been used a lot to study problems in non-relativistic flows. For example, the first investigation of the saturation of the MRI in radiation-dominated plasmas was using flux-limited diffusion, first by Neil Turner, then later by Shigenobu Hirose and collaborators for unstratified and stratified shearing box calculations. And it's used widely in interstellar medium modeling, in protoplanetary disks, in lots of places. FLD is still a method that people use a lot. It's sort of the first and simplest approach that one can take. It has its problems in optically thin regions, as one can imagine, and so people have looked for better methods. And a better method means keeping the flux around as a dynamical variable. A better method is the so-called M1 closure, where it can be derived analytically by assuming that the radiation pressure tensor is isotropic in some rest frame, which is not the fluid frame, but a rest frame in which the radiation flux is zero. If you assume the radiation fields are isotropic in that frame, and you work through the algebra, you can calculate what this Eddington tensor should be in terms of the fluxes and energy densities. And so there's a closed form analytic formula, if you like, for this Eddington tensor, given fluxes and energy densities. And so that makes it, you don't have to solve the transfer equation. You have this ansatz about, you've made an assumption about the geometry of the radiation field, and that allows you to close the system and compute the Eddington tensor analytically. And M1 has become very popular. It's been used, for example, with the first GRMHD simulations of super Eddington accretion flows by McKinney and by Sadowski and collaborators that we used M1 closure. I show you a snapshot from one of their calculations showing you poloidal and equatorial slices of the accretion flow for a radiation-dominated MRI unstable disk calculation. And it's used by many other people as well. It's become a popular method because it's sort of straightforward and has this nice closure and much cheaper than solving transfer equation directly. But there are issues, and as is well known, I mean, the most well-known issue is that in M1, photons kind of behave more like a fluid than collisionless particles. They merge, they collide and merge. Photon rays will merge in M1. And it's easily shown by doing, for example, this shadow test. If you have two beams of radiation, one coming sort of downwards at 30 degrees, one going upwards at 30 degrees, and you illuminate a very optically thick cloud in the middle here, and you look for the shadows that are generated. In M1, the deepest shadow is actually right behind the cloud in the equatorial plane here, even though there should be no radiation going in that direction. But it's because when the photon beams come in, they collide and it generates flux that moves horizontally, and that's being blocked by the cloud and generating the deepest shadow. There are shadows at the right angles, but they're much less than this deep one caused by these merged photon field. The actual right answer is on the bottom here, where you have these two beams coming in and two shadows, one for each beam behind the cloud. This is also an M1 calculation, but it used two different non-interacting frequencies. So it's like doing two M1 problems at once, each one having only one angle to it. So it avoided the collision problem. But it just sort of demonstrates the difference between the two. And so the question is whether this photon collision is really an issue or not. That's a very challenging problem to answer, a very difficult question to answer. Going on with more complicated methods, I would say, the sort of building in complexity. Another approach is the so-called variable Eddington tensor approach, or VET methods, where basically, again, the definition of this Eddington tensor is just moments of the specific intensity over various angles. And so if you can just approximate the specific intensity without necessarily solving it using a time-dependent transport equation, you can approximate the Eddington tensor just by taking these quadratures numerically, and then feed that back into the system of moment equations and integrate the fluid equations. And so several groups have done that in the past. For example, Shane Davis and Yanfei Zhang and myself used this using the time-independent transfer equation to compute I. That's appropriate for non-relativistic flows where the light crossing time is very short compared to anything else. And so you can just assume the radiation field comes to equilibrium and compute the static structure of the radiation field to compute this geometry. But it can also, recently, Monte Carlo methods have been used. MOC-MC is a new method by Ryan and Dolence, which looks very promising. Basically, you're using Monte Carlo to calculate the specific intensity and then take its moments to compute this Eddington tensor and then use the moment equations to evolve the radiation field. So these methods have been used by Yanfei to look at things like corona above radiation pressure dominated disks. These are space-time plots of the horizontally average density in an MRI unstable disk. And you can see the dynamo generating this butterfly diagram, and then dissipation of the magnetic field above the photosphere generates very, very hot plasma. So the bottom space-time diagram is the temperature, and you can see that the highest temperatures are in the corona. You're actually self-consistently generating hot corona above the disk midplane. Again, this calculation was using VET. Then again, increasing complexity, you can sort of bite the bullet and just solve the transfer equation using discrete rays. Just simply discretize the specific intensity over some finite number of solid angles at every grid point. That should be grid, not GID. Just solve the equation using a discretized form for the transfer equation. You need special methods to propagate photons along geodesics in GR, but that's possible. Chris White has a paper in preparation describing methods for doing this. The real issue is that it's memory and compute intensive, and especially memory intensive, because if you discretize it to say, typically we've been using 80 angles at every grid point, that's 80 new variables that you have to evolve at every grid point, and that can be memory intensive. But to show that it works, here's a test from Chris White showing the propagation of beams in a Kerr space-time. You're looking down on a spinning black hole, and the prograde and retrograde beams are behaving just as they should. The green lines are the analytic calculations of the trajectories for the beam, which has some finite solid angle, and you can see the numerical solution is following those trajectories very, very well. So this is clearly doing the right thing in full GR. And the other, of course, way to do the direct solution other than using rays is Monte Carlo. I sort of skipped a slide quickly. I'll just quickly say that this technique of rays has been used by Yanfei to compute a grid of models of radiation-dominated disks from super Eddington down to sub Eddington, from accretion rates 150 times Eddington down to accretion rates of 0.07 Eddington, and there's several papers which diagnose the properties and dynamics of these flows as you go from super Eddington to sub Eddington. So these methods are becoming workhorse. They are feasible to do real 3D MHD calculations with them. So again, then the other way is Monte Carlo. Again, this I nu over nu cubed is the invariant intensity. It's basically the photon distribution function. And so you can discretize this quantity using Monte Carlo packets, photon packets. You can then just propagate those packets along geodesics and have them emitted, absorbed, and scattered according to the microphysics you want to implement. And then you can take distributions or take moments of that of those packets, if you like, of that distribution function to compute the radiation force and the net heating cooling rate on the fluid, and then thereby close the system. So basically use Monte Carlo to solve the transfer equation and then directly compute the forces and heating cooling. It's advantageous because it's fairly simple to have very complex radiation processes implemented. The real challenge is keeping the noise small. If you're doing radiation dominated flows, then even a few percent fluctuations in the radiation pressure will generate waves and turbulence. And so you need to keep the noise below a few percent if you're going to avoid numerically driven dynamics, if you like. And that can be very challenging. Every grid point, you need enough sampling to keep the noise in the moments, not just the distribution function, but the moments of the distribution. And that's challenging. But still, it's being increasingly used. There's a number of well-known codes, Sedona, Blight, and Spec all now have adopted Monte Carlo and are using it to solve applications in radiation hydrodynamics. I wanted to say, while I'm on the methods, one more topic. I mean, I focused on how to sort of approximations for coupling the transfer equation and the radiation hydrodynamics equations. But even once you assume or adopt an approach, there's still skeletons in the closet about how you get this to work. And one of the most important is how you treat the material coupling and material radiation coupling terms. Generally, you need implicit methods because those terms can be very, very stiff, and that'll make the methods unstable without having special treatment. The workhorse method to date is operator splitting, where you solve the transfer equation assuming the fluid properties are fixed, and then you solve the fluid equations assuming the radiation properties are fixed. But that at best is first order. We'd like to do better than that. I'll skip Picard integration, which is a very specific technique that worked well for simple problems, but nowadays implicit, explicit methods look attractive. They're basically standard Runge-Kutta time integration techniques where additional implicit stages are added to build second order, third order, and higher order time integration methods involving implicit substeps. These to date have not really been used in radiation hydrodynamics. The McKinney papers mention them, but don't actually use them in the applications that they present. And so these look like an attractive way forward, but still, I would say that the best strategy to get high order, stable schemes for radiation hydrodynamics is still a matter of research. So let me say something about tests, because they're so crucially important. The only way to distinguish these different approximations and how useful they are is through tests. But then tests are also very hard to construct. And so that's a challenge for radiation hydrodynamics. Generally, tests involve the transport solver or the full coupled dynamics. You want to test both independently. I've shown you some already on propagating beams, but you can also use point sources, distributed sources. And then for the full dynamics, linear waves, which are an exact solution, are an excellent test. Nonlinear shocks are a good test since there's semi-analytic solutions possible. And then instabilities, at least the linear regime, is also very, very useful. So very quickly, here's another radiation transport test developed by Ryan and Dolence, basically a flat plate emitting photons between 6 and 10 M around a Kerr black hole. There's a semi-analytic solution. Here's plotting the radiation energy density from the semi-analytic solution. And here's their MOC-MC method. And again, you can see it's a little bit noisy, but it's converging to the right answer. And conversely, M1 and Eddington give you somewhat different structures, and they don't converge to the semi-analytic solution. And this is, again, this issue of photon collisions and merging. They're not actually representing the radiation transport equation, and they don't converge to the solutions for that problem. And so that whether that's an issue or not, that's a very, very tough question. But linear waves, I've mentioned, are good tests. You set up eigenmodes in three-dimensional periodic domains. You propagate the waves around the domain for a few wave periods. You can measure the phase velocity and damping rate, and compared to the linear dispersion relation, that's what the lines of the analytic solutions, stars of the numerical solutions for different ratios of the radiation to gas pressure. And the beauty is you can measure the truncation error and measure convergence rates, either first or second order, depending on what algorithm you're using. And so that's very, very useful. And even shocks are useful. I mean, the structure of radiation shocks is an interesting problem in and of itself. They're no longer just pure discontinuities. They have smooth precursor regions where photons propagate upstream and preheat the gas, and then cooling regions, relaxation zones. Computing the one-dimensional structure of these shocks is non-trivial. There are no analytic solutions, but now semi-analytic solutions are possible by using ODE solvers to compute the solutions in various regions and then match them with jump conditions where there are true shocks. That's been done by various authors. And then those semi-analytic solutions can be input to dynamical codes, and you can test whether the code holds that solution. Here's an example of a Mach 3 radiating shock. The black points are from the numerical solution, the dynamical solver, and the red line are from the semi-analytic solution. And there's, again, excellent agreement. You can measure errors and convergence rates. And so that's extremely useful. So let me, in the last few minutes, say something about some challenging issues. I think the first is that opacities really matter. And it can be demonstrated by a couple of applications, for example. The inclusion of the iron opacity bump, in addition to electron scattering opacity in accretion disk models, changes their dynamics. Without the iron opacity bump, if you just include electron scattering alone and you do a local shearing box simulation of an MRI unstable disk, you find thermal runaway in some circumstances for radiation pressure disks. You add iron opacity and it doesn't have a thermal runaway. So, and you can diagnose the problem and understand why, but the point is including opacity, realistic opacity, is very important. And another example of that is the need for putting in Compton cooling to get the corona temperatures correct. And maybe even the best example is kilonova, where the lactonide opacities make a big difference as to whether you get red or blue kilonova. So it's clear, including opacities is important. It's something that we all need to try to work harder to do, better opacities. But it's even trickier than that, because most opacities come in tables, opal opacities or opacity project, and they generally provide Rosslyn mean or Planck mean opacities as a function of density and temperature, for example. And there's orders of magnitude difference between these frequency integrated mean opacities. If you plot Rosslyn mean versus Planck mean at different temperatures, you get orders of magnitude difference, which already is worrisome. The way that you take this mean makes a big difference as to what opacity you actually get in the problem. And it turns out that it's neither the Rosslyn mean nor the Planck mean is what you need in radiation hydrodynamics. What you really need is a flux mean, right? What you really want to compute is the integral of the frequency dependent flux times the frequency dependent opacity. That's the radiation force. And so the flux mean times a mean frequency integrated flux is the right mean quantity to be using. And it turns out that flux mean can be very different than the Rosslyn mean. It's been shown for a one-dimensional radiation hydrodynamic calculation of Wolf-Rayet winds, where the transfer equation was solved directly, and then chi-f, which was used in the calculation, was then computed to the Rosslyn mean that would have resulted if they'd taken the Rosslyn mean for their opacities. Again, an order of magnitude difference between the two, which meant that when you do the problem properly, you get a very, very strong Wolf-Rayet wind, and you don't when you get Rosslyn means. And so basically the underlying dynamics changes qualitatively by how you treat the opacities. We really need to do frequency dependent transport and include frequency dependent opacities to be able to estimate these forces more accurately. And it can be very important for some problems. And corollary.
Sorry, Jim, you just got a couple minutes left.
Okay, great. I'll just take 2 more minutes if I can.
Okay.
Another corollary is that photonization is very important. Again, if you calculate a force multiplier by how much the radiation opacities are increased over electron scattering, if you for sort of realistic astrophysical plasma, if you do that in an LTE versus non-LTE, again, you get an order of magnitude difference between the two. And so including photonization is going to be important. And another corollary is that the normal force multiplier used to compute radiation line forces is not going to work in full 3D radiation hydrodynamics. And my last issue would be leveraging exascale. I mean, I think we're in a good shape in the sense that there's very big computers coming online, and that's going to allow us to tackle these very big challenging problems. For example, solving the transport equation using direct methods. But right now, 7 of the 10 fastest computers in the world use GPUs or other accelerators, and that's probably only going to increase. Programming these are complicated. And so fortunately, in the last few years, a bunch of tools have emerged for so-called performance portability, where you can write a single code that works in any architecture you like, for example, Cocos. And we've adopted Cocos in Athena++. It's proved very, very powerful. Our Athena++ will now run on GPUs, CPUs, ARM architectures, any architecture for which Cocos supports, which is basically everything. And it gets excellent scaling and excellent performance on all these architectures. And so I think there are tools emerging that is going to be very helpful for the community and able to leverage these very, very large machines. You're not going to have to write GPU specific code anymore. You're going to be able to run your general purpose code using tools like Cocos. So, and I'll just summarize here. Basically, realistic models of accretion flows requires radiation transport. I think we would all agree with that. And this is a very active area of research. Direct methods are now feasible, and they're becoming increasingly interesting, I think, in the future. And really, my caveats are, even once we get the numerical methods settled, there's a lot of physics to worry about in the opacities and radiation material interaction. And I think we're going to be kept busy for a very long time understanding astrophysical flows and including the realistic microphysics to understand them properly, if you like, or realistically. Okay, with that, I'll finish.
Okay, thanks so much. Let's see, are people looking for, there's some clapping, real clapping, and virtual clapping.
Right.
I'm looking if there are any virtual hands. Or if you want to post a question in the chat. Just to get things started, I guess I'll ask a question about the tests, Jim. I mean,
Sure.
I couldn't agree more about the importance of the tests. But my question is, do we need to limit ourselves to tests with analytic or even semi-analytic solutions, right? I mean, we know that there are, in general, there are methods that are more expensive but more accurate. But for the test problems, they're relatively simple. So why don't we just throw the expensive, accurate methods at them for the ground truth, and then use those to test the other methods?
Absolutely. I mean, I always think that analytic or semi-analytic solutions are the gold standard, because then you have a reference solution against all methods can convergence test against. But you're absolutely right that because there are such limited selection of tests, and they don't test the sort of full 3D complexity of flows you'd like to investigate, it's also very important to compute reference solutions. And that, ideally you want to compute a resolved reference solution that might require putting in explicit dissipation to reach convergence with some sort of direct method or some method that you trust, and then provide that to the community or provide that to your, I think if we can share such tests, I think that's extremely helpful. And I think lots of people do this. They present, their own test problems and their own method papers. And I think that's great, because it inspires and it enables others to try such tests with their own methods, to learn the strengths and weaknesses. Every method has its strength and every method has its weakness. And you simply want to know for your application which one is best suited. Yeah,
and it's especially as we're moving towards an environment where people actually publish codes and share codes, like on GitHub, as part of publications. To put in your own, you can put in your own, scripts about how to run the test for other people to do too.
Yep.
There's a chat from Alexandra in the a question from Alexandra in the chat. Could you please elaborate more on the non-LTE effects? Maybe a couple of examples of where the non-LTE problem or non-LTE effects are most important.
Sure. Yeah, I was getting a little rush for that. So here we're thinking about photoionized plasmas, for example, in the corona or the outflow above accretion disk, and in the very optically thick in the densest regions, then LTE is probably an excellent approximation, because the radiation field is locally, trapped and comes to thermal equilibrium with the plasma within a photon mean free path, which is very, very small. But when you're in the optically thin regions, and now the plasma is being irradiated by photons, which are coming from very disparate locations in the disk, now non-LTE effects can be really, really important. So I'm thinking in the corona and in the wind, where you have an optically thin plasma. This plot is for an optically thin plasma at some temperature. You calculate what the force multiplier would be as a function of temperature, assuming some photonization parameter. So you're radiating it with some spectrum, and then calculating what the opacities would be using LTE and non-LTE. And in that situation, an optically thin plasma, which is being irradiated, then those opacities can be vastly different. And I think that's the region. So people interested in outflows and radiation-driven winds, I think it's where non-LTE effects are probably going to be most at play.
Okay, thanks, Fede. I see your hand, but I think I'm sorry, we have to get on to the next talk for